We're going to go over the intersection of two planes, which is 9.3 in your book. Again, we're going to be dealing with three cases in this lesson to start, okay? Specifically of two planes. Our first case is when the two planes intersect to form a line of some sort, okay? This is our plane 1 and plane 2. The intersection is a vector in space or a line in space. Case 2 is when we have two parallel planes, which means they'll have no points of intersection. And case 3 is when they're coincident planes, or they're the exact same plane. They're identical to each other. So what we're going to do each time we're posed with a question, for instance, we have example 1 here. We're going to check for case 2 and 3 first. If it's case 2 and 3 first, it really limits the amount of work we need to do in the question. Case 1 is when we run into a bit more work. So I've specifically set this up so it's going to be a case 1. But the idea is, for instance, case 3, we're looking for scalar multiples of each other. Okay? So if we look, the idea is a scalar multiple equation may be 2x plus, actually I'm going to write one in. We'll write it in red for case 2, just on the side. The idea would be we have 2x plus 2y plus 2z equals 4. And the other plane would read x, y, z equals 2. These are scalar multiples of each other, which means we have identical planes. Okay? With that being said, case 2 would be very, very similar to that. Case 2, we look at the Cartesian form, and remember these represent the normals, right? The coefficients in front of our variables. Our normals will be identical. The only difference is our constant will be a different number. So an example of that, we'll do in purple here, I guess, case 2. So we have identical normals, so we'll use 2x again, plus 2y, plus 2z, plus 8 equals 0, and 2x plus 2y plus 2z minus 1 equals 0. In this case, the normals have the exact same slopes, okay? Or they have the exact same coordinates, I should say, which means they're going to be parallel to each other. And because this constant is a different number, they're not coincident. Okay? Because it's not a scalar multiple, that means we're looking at case 2. In case 3, we're going to quickly, or sorry, not case 3, case 1, when they form a line, we're going to quickly check to make sure this is the case. So these are both 1, but right away I have a negative and a positive. Okay? These being different, so I'm not dealing with case 1, or sorry, case 2 or case 3. We're dealing specifically with case 1 in this example. It's a lot of saying the word case. Okay, so what we want to do in this question is we want to isolate for variables. Now, because we only have 2 equations and we have 3 unknown variables, we cannot find a specific point in space. We can find equations, and equations would be like an equation of a line. So we'll scroll down a little, give ourselves a bit of room here. In fact, I'm going to move this down. Let's move it down a bit. So what I'm going to do to start off is I'm going to do the same step I've done in the other algebraic questions. I'm going to try to eliminate one of the variables. And looking at it very carefully, if I take a look at, we'll call this equation 1 and equation 2, if I add these together, which variable is going to disappear? Y. Great. I need to eliminate 1. Might as well just eliminate y by adding. So we add them together. Our third equation now will read 2x plus 4z is equal to 0. Okay? Or a little more succinctly, looks like that. Now, because we know we can't solve for a specific point in space, what we're going to do is we're going to give one of our variables a parameter. And the reason we're going to do that is so that we can get a line in parametric form. So I'm going to take the variable z, and I'm going to give it parameter t, since that's a parameter we've been working with a lot. So in our cases, z will always be equal to t. And what I'm going to do is I'm going to set equations equal to x and y, and then finally z in the end. So for instance, in equation 3, I can set it equal to x and plug in t for z. So we get 2x plus 4 We plug in t for the parameter. is equal to 0. We'll get 2x is equal to negative 4t. X is equal to negative 2t. Thank you. Okay. So this is actually the x values in parametric form of our line. We just have to solve the other ones. So we're going to do the same process we did above for all of our other equations here. We'll do the same thing. We'll take those first two equations again, which are x minus y plus 2z equals 2. So this is equation 1, x plus y plus 2z. So here's equation 1 and 2 again. Okay. This time what we'll do is we'll eliminate the x from the equation. So we'll subtract these two. So we're left with a new parameter. When we subtract, these will eliminate. We'll then get negative 2y. Or z will eliminate from this one too. Equals 0. Okay, that made it actually really easy. Okay. And then we'll end up with y equals 0 in this case.
No, it's 4.
Oh, yes, there we go. Thank you. Minus 4.
No, positive 4.
I'll say 4. Minus 2 is our answer. That's better. Thought that was something like that. Okay, so our parametric form of y is just y is equal to negative 2. Okay? And for our z, we can now take these variables and plug them into either the other two equations to solve for z. Since x has a parametric form, we'll be able to substitute z with some value of t. So I'm going to take equation 1, and I'm going to substitute in for x. X is then equal to negative 2t, okay, minus y is equal to negative 2, plus 2z is equal to 2 in this equation. Okay? So let's set this equal to z. Negative 2t plus 2 plus 2z equals 2. When we move it to the other side, we're going to get 2z is equal to 2t. Is that right? Yep. So z will be equal to t. So let's organize our parametric forms here. X was equal to negative 2t. Y was equal to negative 2. Z was equal to t. Okay? And I'm going to put this into vector form so we can kind of get an idea of what we're looking at here. In this case, just to fill it in, we technically have a 0t, which means our direction vector is negative 2, 0, and 1. Okay? And our coordinate, or a point on our vector here, or our line, is in this case, we have 0. So we have 0, negative 2, and 0. So our line where the two planes intersect are at this point here. Now I know they all didn't have a constant in a parametric form, but this is in parametric form right now. We just had to relate it to vector form to maybe make a little more sense of what we had done there.